So welcome everyone to the second week of the program, the discussion meeting. So just an announcement before Professor Hida takes over. So just announcement that the Independence Day, so today is a very proud Independence Day of India. And at 10 a.m. There is a Independence Day celebration in front of the cafeteria. So all are invited and we'll celebrate it duly at 10 a.m. So I hand it over to Professor Hida.
Okay, so I'm the chair of this morning session of the second week talks. And actually, as Somnath told you that there's a celebration of the Independence Day. And this is actually the capturation day of Japan. And anyway, we celebrate it. So let me introduce Professor Shnidman, Hebrew University of Jerusalem. And he talks about sums of two cubes. So please.
Thank you, Professor Hida. Thank you to the organizers for inviting me, and happy Independence Day to everybody there. Yeah, so I'm sad I wasn't able to come in person. My only experience in India was a 3-day wedding in Jaipur. So I'm going to give my best talk so that you'll invite me the next time you do this again. Tell me if you can't see the screen or if there's any issues, and feel free to stop and ask questions. So I'm going to talk about the question of which integers are a sum of two cubes today. This is joint work with Levent Alpoj and Manjul Bhargava. So I'll start with an easier question. Which integers are a sum of two integer squares? Or it's an equivalent question you can ask about which integers are a sum of two rational squares. So this is a very old and famous question, and it has a very clean and nice answer. The answer is it's those integers whose prime factorizations have all primes that are 3 mod 4 appearing with even exponent. And so this goes back to Girard in the 17th century. Fermat, Euler perhaps was the first person to give a rigorous proof. Okay, so that's a question for sums of two squares. So it's natural to ask what happens if we ask about sums of two cubes, which integers can be written as a sum of two cubes, x cubed plus y cubed. Now here I've asked the question slightly vaguely because now it actually matters whether we allow x and y to be integers or more generally to be rational numbers. You'll get different answers based on whether x and y are allowed to be integers or rationals. For example, 6 is not a sum of two integer cubes, but this equation here shows you that it is a sum of two rational cubes. So already the question is going to be a little bit different, and you can see it has a little bit of a different flavor. And okay, the first thing you do is you start computing, and you can check. This is something one can do in principle, is write a list of the first bunch of integers and decide whether they're sum of two rational cubes or not. So 6 is on the list. So this list is those that can be written as a sum of two rational cubes. And if you want to start making some guesses or looking for patterns, you'd probably want to look at a longer list than just this, but you could look at the first 100,000, 10,000 of these numbers. And what you'll find is, unlike the case of Girard, Fermat, Euler, the case of sums of two squares, there isn't a precise rule in terms of the factorization of the integer or in terms of congruence conditions. There's no one precise rule or easy rule that will tell you when an integer is a sum of two rational cubes. And in fact, we don't expect there to be such a rule. And this forces us to change the question a little bit and not ask exactly which integers can be written as a sum of two rational cubes, because there won't be a pithy answer to that question. But we can ask at least how many integers are a sum of two rational cubes, or what proportion of integers, what is the natural density of the set of integers which are a sum of two rational cubes. So that's a question that we can ask. And again, here I've chosen here rational cubes, not integer cubes, because if we do ask the question about integer cubes, then it's not hard to see that 0% of integers are a sum of two integer cubes. And you can argue that if n is x cubed plus y cubed with x and y integers, then x and y have to be bounded in size, and there's a certain bound, and it's not hard to show that a very small, thin set of integers can be written as a sum of two integer cubes. So the more interesting question from this naive point of view of what is the natural density of the set of a sum of two cubes, the more interesting question is rational cubes. So that's what the question is, and the main theorem, main group of theorems is some beginning of an answer to that question. And so our theorem, this is joint with Levent and Mungel. All of this work is joint with Levent and Mungel. And our theorem is that, well, a positive proportion of integers are a sum of two rational cubes, and a positive proportion of integers are not. So this was not known previously, that either of these, that a positive proportion of integers was either a sum of two rational cubes or not a sum of two rational cubes, and this is what we're proving. And we give an explicit lower bound. So more precisely, we show that at least 2 over 21, so that's about 10% of integers are a sum of two rational cubes, and at least 1/6, it's about 16%, are not a sum of two rational cubes. So in terms of sum of two cubes, this is the main result. At this point, like I said, these proportions were not known to be strictly positive, either of them, before this. At this point, you might wonder, well, what should the answer be? And what one would conjecture, maybe I'll explain this at some point in the middle of the talk or at the end of the talk, it's reasonable to conjecture that exactly 1/2 of all integers are a sum of two cubes, two rational cubes, and 1/2 are not, as an asymptotic proportion or a natural density among the set of all integers. Okay, so this is the main theorem, is progress towards this conjecture. We have explicit lower bounds for both directions. We expect that the answer is 1/2 for each, and we have some progress in that direction. So that's the main result. Okay, and by the way, if there are questions, feel free to stop me. It's hard for me to see the Zoom screen if people are raising hands or anything, so just feel free to stop me if there are questions. Okay. So that's the main result, at least in terms of sums of two cubes. And let me now translate what we're really doing into a slightly more modern language. So we're really answering a more general question. So if we care about sums of two cubes, what we're asking about is this equation, x cubed plus y cubed equals n, and whether it has a rational point, a rational solution. And this equation is an affine model of an elliptic curve, of this elliptic curve, where I'm thinking of the rational point at infinity as the identity for the elliptic curve. And so as n, for each n, you have an elliptic curve, and you want to know, does this elliptic curve, or the affine model of the elliptic curve, have a rational point or not? And so it's a family, a one parameter infinite family of elliptic curves. But it's not just an arbitrary one parameter family of elliptic curves. It's what you would call a cubic twist family, because all of these elliptic curves, they're cubic twists of this single elliptic curve, the Fermat cubic. Namely, they're all isomorphic to this one elliptic curve if you work over the complex numbers or over Q bar. Because if I'm allowed to adjoin a cube root of n, then this elliptic curve is isomorphic to the Fermat cubic over the field where the cube root of n lives, which is generally a cubic field. So they're called cubic twists. And so we're asking, really, in this family of cubic twists, this family of elliptic curves, a cubic twist family, how many or what proportion of those elliptic curves in the cubic twist family have a rational point? Or really, we're asking about a non-trivial rational point, because I'm ignoring the point at infinity in these affine models. So that's the more general question. In a cubic twist family, what proportion of twists have a rational point. And our result is in this level of generality. So this result is about a general cubic twist family. So in general, what we can do is we can fix D, an integer, and consider the following family of elliptic curves where I let D is fixed and I let n vary, and I consider for each n the elliptic curve y squared equals x cubed plus dn squared. And we're going to look at statistics in the same sense as the previous slide as n goes to infinity. And the theorem is, first of all, that at least 1/6 of these elliptic curves have rank 0, which is the same 1/6 that you saw on the previous slide. And the second part of the theorem is about rank 1, and we show that at least 1/6 of the elliptic curves in this twist family with good reduction at 2, so there's this extra hypothesis, have rank 1. Not only do they have at least one non-torsion rational point, they have rank exactly 1. Their group of rational points on the elliptic curve is generated by a single element. And so this is the more general theorem. Now, just from the equations, they don't look related, but you can do a little bit of algebra, and you can show that the curve x cubed plus y cubed equals n, this is isomorphic to this particular Weierstrass form, y squared equals x cubed minus 432 n squared. So the sum of two cubes problem, it really is a special case of this more general cubic twist problem, and it's the case where d is negative 432. And if you really want to deduce the previous result from this one, you do have to think a little bit about torsion points, because for the sum of two cubes, in principle, all you need is just any rational point, and torsion would be allowed. But it's easy to see that if I fix D, let's say, then for 100% of n, the torsion group of the elliptic curve EDN of Q, that is trivial. And so there aren't, statistically speaking, there aren't any torsion points in these families that are interesting. And so the elliptic curve has a non-trivial rational point if and only if it has rank at least 1. Okay, so this is the more general theorem that we prove. But even this theorem is really a kind of a corollary, or we deduce it from a more precise result. And so I'm going to spend a bunch of time talking about this result. This is the more precise result that we prove. And it's not a result really about rational points on elliptic curves. It's about two Selmer groups of elliptic curves. So a key ingredient in the proof of the previous theorem is the determination of the average size of the two Selmer groups of these elliptic curves. So again, I'm fixing D, and then I have this elliptic curve for each n, EDN. And for each of those elliptic curves, I can consider the two Selmer group. And I'm assuming here, I'm not going to define the two Selmer group, maybe in the middle of the talk I will, but I'm assuming we're familiar with the two Selmer group. If not, either because we went to the talks last week, or most experts in the audience will just know what this is. Here, I mean the finite, this two Selmer group is not the two primary Selmer group. It's just a finite dimensional F2 vector space. That's what I mean by the two Selmer group. And the more precise theorem is that after fixing D and letting n range over integers, the average size of the two Selmer group is exactly 3. And it's important for these applications, such as the previous theorem, it's important that not only do we compute the average size as n ranges over all integers, we also have the flexibility of computing these averages where n ranges only over integers satisfying a finite set of congruence conditions. And the average is still 3 in those cases, but we prove that theorem as well. And we also prove more general results where we allow certain infinite sets of congruence conditions. You can't just choose any infinite set of congruence conditions. They need to be reasonable enough. So I'm going to use this adjective acceptable, and I won't quite say exactly what it means, but any reasonable set of congruence conditions you impose on n, you'll still get this same average result, that the average size of the two Selmer group, as you let n vary through those integers satisfying the congruence conditions, is 3. Okay, so that's the technical theorem that's going to eventually imply this theorem about rank 0 and rank 1 twists of elliptic curves. But let me just say one thing. One immediate corollary of the Selmer result is that in any cubic twist family of elliptic curves, the average rank is bounded. And what we can show is that, in fact, this is not immediate actually, but that the bound is 4/3. But what we show is that the bound is 4/3. I'll kind of hint to how that works. But in any case, what we show is that the average rank is in any cubic twist family is bounded by 4/3. But in particular, it's bounded. That wasn't known before either. It's the average rank that's bounded. We're not claiming to prove that the rank itself is bounded, is uniformly bounded or anything like that, but the average rank is bounded by 4/3. And a corollary of this corollary is that in general, the average rank in any twist family of elliptic curves is bounded. And this is because there are only 4 kinds of twist families of elliptic curves, and cubic twist families are the last ones where it was an open question whether the rank, the average rank, was bounded. And since we're covering this case now, this corollary is known. So quadratic twist families have been handled by Smith in the generic case with his recent preprint that he put on the archive recently, and certain cases by Bhargava-Ho, Lemkelver, and myself. The cubic twist case is what I'm talking about today. The quartic twist case is a result of Kane and Thorne. This is a single twist family, J invariant 1728. And the sextic twist family, this is also a single twist family, J invariant 0, and this is a result of Bhargava-Ho and myself from a few years ago. So putting it all together, we see that in any twist family, the average rank is bounded. I say almost in parentheses because there are actually a few cases of quadratic twists that last I saw Smith's method don't quite handle them, and our method also doesn't handle them. So there may, and I don't know whether those cases have been handled by Smith in his most recent preprint. I didn't look carefully enough. So there may be a few degenerate quadratic twist families where this is not known, but aside from those, this is now known. Okay, and I should say each of these families, the methods are different, or at least somewhat different. The quadratic and quartic are very different from cubic and sextic, and for each one you really need a different argument to prove the result. Okay, so this is on just some immediate corollaries of this theorem. For the rest of the talk, the plan is I want to explain how to deduce from the average result that the average size of the Selmer group, the 2 Selmer group is 3, how to deduce that the theorem about rank 0 twists and rank 1 twists. And then I'll try to also then sketch a proof of this technical result, which is the main meat of what we're doing. As you'll see, we're going to use a bunch of big machines to help deduce the main results, but then in terms of the main technical results that we're proving, it's this average result, and I'll sketch a proof of that as well if I have time. We'll have to see. Okay, any questions? I don't know how easy it is for people in the audience to ask questions, but I'll just stop here and in case there are any questions, and also to give myself a little break from talking. Okay. So now I want to explain how you go from this average size result to proving this theorem that 1/6 of elliptic curves in any cubic twist family have rank 0, and at least 1/6 of elliptic curves with good reduction have rank 1. Okay. So, right. We're fixing D because that's what fixes the cubic twist family. So D is fixed and N is varying, and so I'm going to drop the D from the notation and just call the elliptic curve En now, at least for a little while. I'm going to do this. So En is this elliptic curve, y squared equals x2 plus dn squared. And the 2 Selmer group sits in this exact sequence between this E mod 2E the weak Mordell-Weil group and the two part of the Tate-Shafarevich group. And so if you can bound the size of the two Selmer group, you can bound the rank of the elliptic curve. And so it's an immediate corollary of the result that the average size of the two Selmer group is 3. It's immediate, as I said, that the average rank is bounded. Now, what you get from a naive, what's immediate is that the average rank is bounded by 3/2, by 1.5, not the 4/3 I said earlier. And here's a hint in parentheses for how you deduce this. Maybe I won't go over it and just let you think about it, but this is, I think, Arul in his talks last week probably showed this trick. And so you immediately deduce, if the average size is 3, that there have to be many elliptic curves with small rank. And in particular, there certainly a positive proportion need to have rank 0 or 1. But one observation, and probably came up in Arul's talk last week also, is that this is not enough to conclude that there's a positive proportion of twists that have rank 0. And it's also not enough to conclude that there's a positive proportion of twists that have rank 1. It's enough to conclude that there must be twists of rank 0 or 1, but for the original problem of sums of two cubes, it's not, you don't want to know whether there are twists of rank 0 or 1. You want to know whether there are twists of rank exactly 0 and whether there are twists of rank exactly 1. And it's not enough. So for example, this fact that the average size of the two Selmer group is 3, it's consistent with there being 50% of elliptic curves having rank 1 and 50% having rank 2 and 0% having rank 0. And you could come up with another distribution consistent with the fact that there is 0% with rank 1. So we need to do more to prove that there are rank 0 twists and rank 1 twists in these families, even beyond proving that the average size of the Selmer group, the two Selmer group, is 3. Okay, and so what we'll do, and this is similar perhaps to what Arul was talking about in his lectures, is we're going to analyze the root number. And so let Wn be the root number of En. So it's either +1 or -1. It's the sign and the functional equation of the completed L function for the elliptic curve. And so we have this nice functional equation. And of course, BSD tells us or predicts that the rank of the elliptic curve should be the order of vanishing of the completed L function at the central point, s equals 1, the way I've normalized it. And a consequence of that, so a consequence of BSD, is that the root number, if you think a little bit about the sign of the functional equation, a consequence of BSD is that the root number Wn should be equal to -1 to the rank. So it should tell you the parity of the rank. If the root number is 1, the rank should be even. If the root number is -1, the rank should be odd. In particular, the rank should be positive. But of course, the parity conjecture is open. It would be nice to know the parity conjecture because we can analyze the root number. That's something we can get our hands on, and so that would tell us something about the rank. But the parity conjecture is open. BSD is open, and even the parity conjecture is open in general. So what we're going to use instead is not the parity conjecture, but the p-parity theorem. So it used to be called the p-parity conjecture, but it's been proven by Dockschitzer and Dockschitzer, as well as by Nekovar. And what does this say? This is related not so much to the rank, but to the rank of the Selmer group, which is conveniently for us, that's actually more relevant for us in some sense. And it says that if you have an elliptic curve E over Q, and if W of E is its root number, then the root number is equal to -1 to the dimension of the Selmer group, the P Selmer group, plus the FP dimension of the P torsion. And so we're going to use this as a very non-trivial theorem. We're going to use this result in the case where P is 2. And in our family, we're using it with P equals 2 and the elliptic curves in our family. And as I said, in our family, and the torsion subgroup is trivial almost all of the time. And so what this formula says is that Wn is -1 to the F2 dimension of the two Selmer group. At least for 100% of integers n, so that's what's relevant for us. So Wn tells you, conjecturally it tells you the parity of the rank. Provably it tells you the parity of the dimension of the two Selmer group. Okay, and so this is what we're going to use, and we're going to use it by proving things about the root number. So what we prove is that the root number is equidistributed in this family. So that's the first thing that we prove, that 50% of the elliptic curves in this family, in any one of these cubic twist families, have root number +1, and 50% of them have root number -1. That's what this theorem says. And in fact, this theorem says something stronger, and it's crucial that we can say this more, the stronger result, that even if you impose congruence conditions, you still have equidistribution of root number, at least if your congruence conditions are with moduli that are prime to 3. And this prime to 3 is, so 3 is relevant because these elliptic curves all have bad reduction at 3. All of them do. No matter how you twist, you always have bad reduction at 3. And it's important, this caveat, because it's just not true if you drop the caveat. And in fact, there's this other theorem that I'll put on the slide, which is in some sense kind of the opposite type of theorem. It says that if you fix a sign, so let's say we fix +1, and we look at the subset of integers where the root number is +1, that's a kind of complicated set of integers. It's not cut out by like very simple congruence conditions. It's cut out by very complicated kinds of conditions, but you can write it as a countable union of what we're calling acceptable sets that are defined by reasonable congruence conditions. And so it's saying that on the one hand, if you use prime to 3 congruence conditions, the root number is equidistributed. On the other hand, if you manipulate your congruence conditions appropriately, you can actually restrict to subsets where the root number is constant. So I think the simplest example of this, I didn't put it on the slide, but the simplest example is if n is square free and 1 mod 9, then I believe in the sum of 2 cubes family, the root number is +1. That's congruence conditions, like being square free is infinitely many congruence conditions, and 1 mod 9, that's a congruence condition, mod 3, mod power of 3, and so you get in that case that it's a constant, the root number. If you were to impose only prime to 3 congruence conditions, it's always going to be equidistributed. Okay, and we prove this by, there are explicit formulas for root numbers, in this case, due to Rohrlich, Virilli, Alvarado. You can work them out yourselves, actually, just using Tate's algorithm. These are well-known formulas, and in this I've given you up to some factors, some fudge factors. This is the formula for the root number. It's -1 to the number of primes, essentially the number of primes that are 2 mod 3 dividing n, where you count without multiplicity. So if p squared divides it, then it's still just counted as 1 prime, and the same as if p divides it exactly. And so this theorem amounts to it's a theorem in analytic number theory. We use the Selberg-Delange method. It's a little bit messy to handle the prime to 3 congruence conditions, but it's a kind of a fun and somewhat complicated analytic number theory problem. Okay, and so I won't go more into the proof of these theorems, but we'll now use them in conjunction with this p-parity conjecture, and I'll show you the proof of the first part of that theorem, that at least 1/6 of the cubic twists have rank 0. So here's how the proof goes. Consider the set of integers n where the root number is 1 and not -1, but +1. Now, that is by this previous theorem, that's a countable union. S is a countable union of acceptable sets. In other words, our theorem applies to it, and therefore the average size of the Selmer group is 3, because we're assuming this result for now. And fine, the average size of the Selmer group is 3, but by the 2-parity theorem, these Selmer groups are all even dimensional F2 vector spaces, and so their sizes are even powers of 2. So it could be trivial, in which case the size is 1, but if it's non-trivial, its size is at least 4. If it's not 4, then it's at least 16, etc. And it's easy to see that if the average is 3, well, that means because the next biggest size bigger than 1 is 4, it means that a positive proportion have to be trivial. So this is the argument, and you can quantify this argument. It actually means that 1/3 of the twists need to have trivial Selmer group, and here I'm giving you the equation that you would use to quantify that, to quantify that argument. Q stands for the probability that the Selmer group is trivial. And so, yeah, so there we're using this 2 parity theorem, and that's on the only on the set S of numbers of integers n where the root number is +1, but we showed that that root number is equidistributed, so that set has density 1/2. And so on a density 1/2 set, there's a 1/3, at least 1/3 of the elliptic curves have rank 0, so altogether at least 1/6 of the curves have rank 0. So that's a sketch of the proof of the first part of the theorem, that at least 1/6 of elliptic curves in any cubic twist family have rank 0. Okay, any questions so far? Otherwise, I'll just keep going, but want to give the opportunity for questions or comments.
Sorry, is there a typo, like at least 1/3 have 2 Selmer trivial? Or
say that one more time.
the 4th bullet point is the mod 2 Selmer of En as rank. Sorry, the cardinality is 1. So sorry.
Yeah, does that make sense now? Did you understand, or is there still a question?
I misread it as a rank, F2 rank, so sorry.
Okay, yeah. So I will all the time go back and forth between size and F2 rank, so I apologize for that. But you know, sometimes one is more relevant, and sometimes the other is. Okay, now you can do the exact same thing with the root number -1 twists. So you look at that subset, which is again a density 1/2 subset, and again our theorem applies. So the average size of the 2 Selmer group on that subset is still 3, and so by the 2 parity theorem, and by the 2 parity theorem for any n and s in this set, the dimension of the Selmer group is actually odd, and so the sizes are possibly 2, 8, 32, 128, etc. And again, if the average is 3, well, that means the only size less than 3 is 2. The only valid size less than 3 is 2. So it means that a positive proportion must have size 2. And you can quantify that argument, and you get that at least 5/6 of those elliptic curves have 2 Selmer group, which is rank 1 2 Selmer group, or dimension 1 2 Selmer group. But in terms of sizes, that means that the size is 2. And here again, I'm showing you the equation you use to quantify. And great. So again, because this was a 1/2 density set, we've just argued that 5/12 of all elliptic curves in the family have Selmer group of rank 1, have 2 Selmer group of rank 1. But now the question is, if you have an elliptic curve and its 2 Selmer group has rank 1, or in other words, its 2 Selmer group has 2 elements in it, then is the rank of the elliptic curve equal to 1? And I phrase it this way because we want to say that that's true. And it is true if you assume the finiteness of the Tate-Shafarevich group, because of this exact sequence. If the Tate-Shafarevich group is finite, then we know that by the Cassels-Tate pairing that the 2 part of the Tate-Shafarevich group is an even dimensional F2 vector space, and it follows that the rank of the Selmer group should agree up to parity with the rank of the elliptic curve modulo torsion, but we're ignoring torsion, so we really get it. And so yeah, so if you assume the finiteness of the Tate-Shafarevich group, then this should be true. So we expect this to be true. But given, that's another question, like what can we actually prove? And currently, as far as I'm aware, in the current state of technology, this isn't known in general. It's known in various kinds of cases, but not in general. And so it's not clear how to get to this. We need an extra tool to prove the second part of the theorem. And so at some point we asked Ashay and Chris Skinner, Ashay Burungale and Chris Skinner, who are working on exactly these kinds of p-converse theorems, where you can prove statements like this. And even though the theorem is not in the literature, they are able to prove this theorem. And so it's going to appear as an appendix to our paper. So this is the following p-converse theorem of Burungale and Skinner that we're going to use. So it says that in certain circumstances, you can deduce this fact. So this is known, there's, I think Francesc is discussing, if I'm not mistaken, maybe last week he already discussed theorems like this. His theorem that he was discussing, this is work with Skinner, Lee, Grossi, doesn't quite apply to our situation. So somehow our situation escaped all of the known results, but Burungale and Skinner, they proved this result in the case of a CM elliptic curve with supersingular reduction at P. And they show that if the P Selmer group has rank 1 and the localization map is injective from the Selmer group to the local Selmer group is injective, then indeed the rank is 1. So they prove this theorem in certain circumstances. So note in particular, there's a good reduction hypothesis here because they're demanding supersingular reduction, in particular good reduction. And of course, they're also demanding that the elliptic curve be CM. That's fine in our case because our curves all have J invariant 0. They all have complex multiplication. And the prime 2 is inert in the CM field in our case. The CM field is Q adjoint square root minus 3. So if the elliptic curve has good reduction, it will have supersingular reduction, but it's not that not all of these twists will have good reduction. Luckily for us, in the sum of 2 cube case, when D is minus 432, there are lots of curves in the family with good reduction. 4/7 of them have good reduction. Good reduction basically means when n is odd, and maybe one other case, but it's essentially that n is odd. And so some of the elliptic curves will satisfy this good supersingular reduction hypothesis. You then need to make sure that these other 2 hypotheses are satisfied. Of course, there's this assumption where we already had like 5/6 or 5/12 of curves satisfying that assumption, but then there's this additional one. And so we can incorporate this assumption into our methods, but it means that the proportions drop. And so instead of 5/12, instead of 5/6, you drop down to 1/3. That satisfy both of these conditions. That's something we can prove by incorporating this condition into our argument. And altogether, when you compute the various proportions here, so 1/2 for root number, 1/3 for this computation that we did, and then 4/7 for good reduction, you get this number 2/21. Okay, and just a note is that in general, so this is for D equals minus 432. This same kind of thing will work for many D, for lots of D, but not all D. There are certain cubic twist families where none of the elliptic curves have good reduction at 2. And so this question is open still for cubic twist families, whether there always exists a positive proportion of elliptic curves with rank 1 or even positive rank. That's still in those families where there isn't good reduction at 2, I guess it's open. One would hope that Ashay and Chris and their collaborators, we're hoping that they prove a more general version of this p-converse theorem in the next few years, and then these assumptions hopefully will become less relevant, and then our proportions would correspondingly grow up to 5/12. But for now, we're stuck at these smaller proportions, about 10%. Okay, so that's how you deduce the theorems about rank 0 and rank 1 twists, and the main theorem at the very beginning about sums of 2 cubes from this result that the average size of the 2 Selmer group in any cubic twist family is 3. So that's a sketch of how you do that. So for the remaining bit of the talk, I'm going to sketch the proof of this result. So it seems like I probably have about 20 minutes. That's what I'm looking at. So tell me, or I don't know if I'm supposed to stop for questions, Somnath, but maybe I'll give myself 15 minutes or something. Okay, so this is what we want to prove, that the average size of the 2 Selmer group is 3. So first, let's back up a little bit and finally maybe say something a little bit more about the two-Selmer group. So in general, let E be an elliptic curve. There are many different ways to think about the two-Selmer group. I kind of want to use all of them. So I'll just give two. One way to think about the two-Selmer group is it parameterizes certain geometric objects. It parameterizes isomorphism classes of pairs C and D, where C is a genus 1 curve whose Jacobian is E, is isomorphic to E. D is a degree 2 divisor on C, but we think of it up to linear equivalence. And the third crucial property is that the curve C needs to be locally soluble. So it needs to have QP points for every prime P. It needs to have a QP rational point for every prime P, including P equals infinity. So it has to have a real point. Okay, so this is one kind of an algebro-geometric way to think about the two-Selmer group. It doesn't tell you the group structure really, but it's a way to think about it as a set. Cohomologically, we could define the two-Selmer group as the kernel of this localization map on group cohomology. Localization and then pass to E, from E2 to E. So what I assume most of the people have seen this latter description. The main thing I want to take out of this is that the Selmer group is a finite subgroup of this infinite dimensional F2 vector space H1Q E2. The E2 is the two torsion subgroup of E. I'm thinking of it as a Galois module or as a group scheme over Q here. Okay, so this is the two-Selmer group. And as in last week's lectures, I think Arul talked about this famous classical now parameterization of two-Selmer elements of all elliptic curves in terms of binary quartic forms. And there are other kinds of parameterizations and we're going to use one of them. So there's this especially beautiful one of Bhargava-Ho from about 10 years ago, where they consider the group G SL2 squared, and they let G act on the space V of pairs of binary cubic forms. Yeah, so this is an 8-dimensional, so these are binary cubic forms, so they're homogeneous cubic polynomials in 2 variables, so each one has 4 coefficients. So it's 8-dimensional, this vector space V, and G is acting in the kind of obvious way where it acts on the 2 variables in the binary cubics simultaneously, diagonally, and it also it acts on the binary cubics in an outer fashion by taking linear combinations of the binary cubics. But and more abstractly, V is this representation, symmetric cube of the standard, tensor the standard. Okay, and this is a small enough group and small enough representation that its invariant theory is very well known, and everything about it has been computed. Over the complex numbers, it has 2 free invariants. So the ring of G invariant functions on V is freely generated by 2 polynomials in the coefficients of F1 and F2. They're called A1 and A3, and they have degrees 2 and 6. So A1 is a homogeneous quadratic form. It's a quadratic form in the coefficients of F1 and F2. And A3 is degree 6 in those coefficients. Okay, now why is this relevant to 2 Selmer elements? Well, because according to Bhargava-Ho, they explain that there's a very simple, nice way to construct well, something that's at least a genus 1 curve from a pair F1 and F2. Namely, you consider the generic linear combination of F1 and F2. So you take formal variables, X1 and X2, you take the linear combination, and you compute the discriminant of this cubic polynomial, thought of as a polynomial in the original variables, X and Y. That discriminant is going to be a quartic polynomial in the new variables, X1 and Y2 and X2. Sorry, let me turn off my flux. Something funny is going on. Okay. Hopefully. Okay. And sorry. My screen is turning all yellow, so I just want to turn this off. Okay. I don't know if it's turning all yellow for everybody there. Okay, I'll just go through with it. So
looks fine to us.
okay, that's fine, as long as it's good for you. So from F1 and F2, you can construct this binary quartic form, and you can just set z squared, z is another variable, you set z squared equal to that binary quartic. This is a hyperelliptic curve. Z squared equals a quartic, and it's genus 1. Z squared equals 4, it's a genus 1 curve. It's a genus 1 curve, it's hyperelliptic, so it comes with a degree 2 divisor, a linear equivalence class of degree 2 divisors by pulling back a rational point or a degree 1 divisor on P1. And so we get a curve, a genus 1 curve with a degree 2 divisor. And we'll say that F1 and F2 are locally soluble if that curve is locally soluble, if it has QP points for every prime P. And so in this way, at least for locally soluble vectors, F1, F2 in V, you get a 2 Selmer element of its Jacobian. Of whatever the Jacobian of C is, you get a 2 Selmer element of its Jacobian. And what they show is that this is a bijection. You get a bijection. So let E be the elliptic curve for any elements in Q, A1 and A3. Let E be the elliptic curve y squared plus A1 xy plus A3y equals x cubed. Then if you consider only the locally soluble pairs, F1 and F2, with integer coefficients and whose invariants are A1 and A3 for these numbers, A1 and A3, then the G of Q orbits of those F1 and F2 are in bijection with the 2 Selmer group of that particular elliptic curve E. And the map from right to left is the one I've just described. Given a locally soluble F1 and F2, I've just described the 2 Selmer element of the Jacobian, and the claim, part of the claim here is that this is the Jacobian of that curve. So this is their theorem. There's, to prove the theorem, you have to do various things. You have to show that this map is injective, surjective, and a crucial part of the theorem, important information here is that this works for the integral locally soluble vectors. So all the Selmer elements correspond to F1 and F2 that are integral or that have integral representatives. There's an integral element in the G of Q orbit of F1 and F2. Okay, and one thing to observe is that this family of elliptic curves, E, A1, A3, this is some very natural, very nice family of elliptic curves. It doesn't have every elliptic curve in it, though. It's the universal family of elliptic curves with a point of order 3. So every elliptic curve with a point of order 3 can be put in this form and in a unique way, essentially. So okay, this is what they prove. Very pretty bijection. And so we're going to use this, but we don't care about all of these elliptic curves. We care about a very specific kinds of elliptic curves. And so what we're going to do is we're going to look at those elliptic curves where A1 is 0. So in other words, where little a1 is 0. We're going to focus our attention on those. And so another way to do this is just consider inside V the subvariety defined by setting this degree 2 invariant equal to 0. It's a degree 2 invariant. So what you get is a G invariant quadric inside of this 8-dimensional space. And on that quadric, we're going to look only at that quadric. And on that quadric, there aren't 2 invariants anymore because one of them by definition was set equal to 0. So there's really only one invariant, and we just call it the discriminant. So we'll call A3 of y for y in the quadric the discriminant. Okay, and so one thing you can do is you can just restrict the Bhargava-Ho parameterization to the quadric. And so you just get this theorem that for this elliptic curve here, what I'm calling En is what you get when you set in the previous theorem, what you set A1 equal to 0. And I'm calling A3 now N. And so you get a bijection of the exact same type just by restricting the previous bijection. But now you observe that this En, this is a family of cubic twists. You can see it's a family of cubic twists. Well, maybe a little bit of algebra to really see that it's a family of cubic twists. But with some algebra, you check that En is isomorphic to this particular family of cubic twists. It's what I was calling EDN earlier, where D is 16. And this is exactly the cubic twist family where there is a point of order 3, a rational point of order 3 in the family. Okay, and so this is interesting. We have a way of parameterizing two Selmer elements in this one cubic twist family. What we'd like is a general way to parameterize two Selmer elements in any cubic twist family. The problem is that a general cubic twist family just will not have a 3 torsion point in the entire family. There will be no rational 3 torsion point in general. It's only first when D is a square where you'll actually have a 3 torsion point. And so the general cubic twist family just will not appear. Its two Selmer elements cannot be written in this way. Their genus 1 curves cannot be written in this way. But we're going to use this representation anyways. And the trick is to observe that if you look at the 2 torsion group EDN2, it is isomorphic to the 2 torsion group of some elliptic curve in that one very special cubic twist family. Namely, you look, it's a funny little thing, you just go and compute that it's isomorphic to the 2 torsion group of E2D squared n as group schemes, as Galois modules. The way you see, you just write out what the elliptic curves are, and you see that the cubic polynomials give you the same cubic fields. The right-hand sides of the 2 cubic Weierstrass forms, they give you the same cubic fields, and that immediately tells you that the 2 torsion group schemes or Galois modules are isomorphic. And so it tells you that their H1s are isomorphic, and that tells you that their Selmer groups, which live inside of their respective H1s, can be compared, and you can hope that they're connected to each other. And in fact, what's true here is that this curve EDN is the dth quadratic twist of this curve E2D squared n. So you can even hope for something even stronger, that there's a direct way to go from a geometric way to go from this H1 to this H1. And so this suggests the following construction, or I'm just jumping to the definition actually. We'll say, so remember now we fixed D. D is fixed. And I'm going to define a different notion of local solubility on the same vector space V. I'll call it D locally soluble. So we say F1, F2 is D locally soluble if this curve is locally soluble. So I'm twisting the genus 1 curve by D. And if you think about it, this, or another way to say this is, instead of z squared equals disk f1 x1 f2 x2, I'm doing z squared equals 1 over d times discriminant f1 x1 plus f2 x2. But notice that you can't, I'm just scaling by d, but I can't get that by scaling f1 and f2 or something like that. Like, this is a genuine new construction that doesn't arise naturally from the old construction with a pair of binary cubic forms. If you scale f1 and f2, the discriminant will scale by a 4th power or something like this. And so these curves don't arise from the previous construction, but they're just these simple twists. And so what we'll do is we'll show that now there's a bijection between this funny notion of locally soluble vectors f1 and f2 in the quadric still with the 2 Selmer group of EDN. And so again, the map from right to left here is just this construction. Given f1 and f2, that's D locally soluble, and with integral coefficients, I've given you a genus 1 curve that has a degree 2 divisor on it, and because it's D locally soluble, the curve is locally soluble, and so it gives you an element of the 2 Selmer group of some elliptic curve, and we're claiming that that elliptic curve is EDN. And we're claiming that it's a bijection. And so if I have time, I'll explain how to prove this, but for right now, we'll assume this theorem. This gives you a map in one direction, but it's not clear how to write down a map in the other direction. Not totally clear how to write down a map in the other direction. But let's assume this parameterization for now. If we assume the parameterization, notice how the discriminant here of the the pair of the f1, f2 is 2d squared n. Now d is fixed and n is varying. And so we're just, 2d squared is just some constant and n is varying. And the discriminant matches up with the n that's going to infinity in our average computation. And so what it means is that we've reduced the original problem of computing the average size of the two Selmer group of EDN to a completely different looking problem, the one of counting the number of G of Z orbits on a G invariant quadric in some G representation with bounded discriminant or with bounded invariance and satisfying certain congruence conditions. Namely, there's a congruence condition on the discriminant, and there's also congruence conditions on the forms F1 and F2 themselves. We only want the locally soluble ones. But that's a clean translation from the original problem, given this theorem from the original problem to this counting problem of G orbits in a G invariant quadric. And what we do is we prove in general, we give a general result for how to do that counting problem. This theorem is just kind of a vanilla version of it, where this theorem is just telling you how many G of Z orbits on the quadric there are with bounded invariant. And we give it, there's an interpretation here of the formula. It's in terms of local density. So if you want to impose congruence conditions on the discriminant, then you can do that. And the result you get is it's some constant times X times some local densities, both Archimedean local density and a p-adic local density. And these are in terms of natural measures on the quadric that you can define in a natural way. So let me say a few remarks on this counting theorem. This theorem has nothing to do in principle with Selmer groups. It's just a theorem about counting integral orbits on a G invariant, on this particular G invariant quadric. And the way we prove this is using the two tools. The main tools are Bhargava's averaging method, so the usual geometry of numbers methods, but those are usually for integral orbits inside of a representation, an affine space. And we combine it with the circle method, which is designed to count points, rational points or integral points on a quadric. And so we're combining these two methods somehow. And so the idea here doesn't originate in this paper, in our paper. This goes back to Sam Ruth's thesis, and then more recently Levent's thesis. So it's really, Levent has a general method of doing this, and to get the strong enough results, we have to improve his results a bit and generalize them a bit to get the strong enough results. So I refer you to talks of Levent on these results that I'm describing today for more details on the counting aspects. There's some videotaped talks. Now here, there's a technical thing here. We're counting irreducible orbits, which means that the quartic form has no linear factor, but those orbits exactly correspond to the identity element of the Selmer group, and so that's fine. We want to restrict to those in some sense because we know how to count the identity. And for the Selmer group application, you need something more general than just this theorem. There's no mention here of Selmer groups or general congruence conditions, so we have to beef up the theorem. So we have to prove a more general version where we allow congruence conditions not just on the discriminants, but on the forms themselves, on F1 and F2 themselves. And we also have to weigh the counts in a certain way because we want G of Q orbits, not G of Z orbits. But this is kind of technical stuff that's known. This is a more standard kind of thing. Once you have a counting theorem like this, it's pretty standard to deduce these more general versions if you can prove a uniformity estimate, which is part of what we do. And another standard thing is when you try to compute what all these local densities actually give you in the case of Selmer group conditions, you find that the Euler product, it outpops the number 2, and adding 1 for the identity element gives you an average of 3. And so that finishes a sketch of this average Selmer result, and together with the earlier arguments, a sketch of the the results I gave at the beginning of the talk. I was going to talk about the proof of this parameterization theorem and generalization to higher dimensional abelian varieties, but I don't know when I started exactly, but it's been an hour since I was supposed to start. So I think I'll stop here and see if people have any questions. Thank you.
Because of the celebration, I was told that I need to cut off the question within 10 minutes or something. Please ask questions concisely in a clever way. Is there any question?
Can n range over prime, say one congruent to congruent to 1 modulo 9? So then we know the root number is 1 and rank is at most 2.
Yeah, so if you just restrict to primes n, then this becomes what people call Sylvester's conjecture. I think Daniel Chris, it's a different kind of question. Yeah, it's a different kind of question. Our methods don't say anything about that question because we're not able to sieve down to primes. That's too much sieving. We're not able to do that kind of thing. But Daniel Chris has a preprint where he announced a proof of Sylvester's conjecture. I don't know. Yeah, so it seems that the analogous question there has been proven, but I don't know the details. I haven't looked at his preprint.
Okay, but can you say say something about the put congruence conditions on the prime factors of n?
Like what kind of theory? What kind of thing would you like to say about them?
Say, for example, all prime divisors are 2 modulo 3, or
like you want to look at just n where all primes are 2 mod, all primes dividing are 2 mod 3, that kind of thing. Yeah, you might be able to say something about that kind of family. That's still like a thin family, and so it's not immediate from what we do to prove anything about such families, but it's possible with like more delicate analysis of error terms and the uniformity estimate that I didn't talk about it, but it's hiding and all of the counting. It's possible you could try to say something, at least like an upper bound, for example, on the average being 3. A lower bound might be harder. I don't know actually, but we don't prove things like that. You can definitely take our tools and try to prove things like that, but it will involve more analysis than I'm comfortable with. So.
Thank you.
Okay, so 10 minutes is almost. Is there any other question?
I had a question. This was new to me, this parameterization of the 2 Selmer group for the universal family with a point of order 3. There are quite a few universal families, like you can take the curves with a point or the marked with 2 marked points or a marked 2 torsion point. Is this the only one where a Selmer parameterization is known?
No. So you should look at Wei-Ho's paper with Bhargava, the Bhargava-Ho, their paper, and they prove many parameterizations of that type. And so in the universal family with a marked point, they prove a result that the average size of the 2 Selmer group is what you expect it to be. I think 12 or whatever, maybe 6, whatever you expect it to be. So there's some list, there's some finite list in her paper with Manjul. I don't remember all of them, but there are definitely other examples. Yeah.
Thank you.
Any other question? There's one more question, perhaps.
Hello. Yeah. So can you say about this equation over a quadratic field or any number field? Like suppose you can write any ring of integer of any number field in terms of sum of two cubes, or basically over quadratic field. Can you say?
Okay, so the question is, can we say anything about the sum of two cube question, but over larger number fields?
Yes.
I don't know, because one thing you would need is all of the machinery of the circle method, Heath-Brown circle method, which as far as I understand from Manjul and Levent, like in principle, it should exist. It's just not clear it's all been written down, some of the basic circle method stuff over number fields. So I don't know. What I'm gathering from them that in principle, you should be able to do something, but there may be technical issues with trying to do it.
So one more question. So can you just change the equation, like so same equation, like you can write the integers in terms of sum of one cube and one square, like x cube plus y square equal to n. Can you find density of such integers n?
Yeah. So that's if you look at the equation y squared equals x cubed plus n, that is the sextic twist family of all J invariant zero elliptic curves, and we in Manjul, Bhargava-Elkis and I already proved results of that type a few years ago. They're not stated quite as strongly because Francesque, the Castella, Skinner, Grossi, Lee result didn't exist yet, so we couldn't prove rank 1 results. But nowadays there are rank 1 results in that family also. Yeah, so we have results like that already.
Thank you.
So it's a pity that I need to cut off the question here, but perhaps the speaker is willing to answer questions once you send an email or something to him.
I'm very happy to answer questions, yeah.
So let's thank speaker again.
Thank you very much.